Yeah, so we tried out the different aggregation functions to find the best that kind of maximize the correlation with the actual new plane close-up score, which ensures that our pseudo simulation can actually approximate the close-up simulation pipeline. We tested different rule-based and learning-based planners on our pseudo simulation framework and compared the pseudo simulation score with the actual close-up score. The y-axis on the plot here is our EPDMS metric that we use in our pseudo simulation framework. And the x-axis is the new plane close-up score. We found the R-square of our approach is around 0.8, which surpassed the best existing open loop simulation approach, which is like the previous NavSim approach. So yeah, as a summary, by using both real-world data and pre-generated synthetic rendering data, we're now able to perform parallel model inferencing that is usually only seen in open-loop setting. But at the same time, because we use some pre-generated synthetic observations, we're also able to embrace the benefits of testing compounding errors and causal confusion that are usually present in those expensive and interactive closed-loop simulation environments. I want to take a moment to thank to my wonderful team, although some of them cannot come today. The project and organized challenge would not have been successful with my amazing collaborators. The next phase of the challenge will be held in ICCB this year. For more details about our pseudo simulation paper and our workshop, please feel free to scan the QR code here. The submission deadline for our next round of challenge is September the 20th. And we'll give out prize on Innovation Award, Outstanding Champion, and also travel grants to the teams. Please stay tuned for more details in the coming months. Oh, sorry. There's two final slides. So at the end, I just want to kind of express sincere gratitude to all the active participation in the challenge from all the teams around the world. We saw a lot of interesting solutions this year, and we're certain that they'll help push the development of end-to-end driving forward. And I'm glad to announce that the champion team this year for our CVPR 2025 challenge is from NVIDIA with the high score of 49.11 on the leaderboard. And now we'll welcome them to present their approach.
Okay, so please welcome Team NVIDIA to present their work, GTRS, Generalized Trajectory Scoring for end-to-end multimodal planning.
Hey everyone, I'm glad to present our the champion solutions GTRS generalized trajectory scoring for end-to-end multimodal planning. So we can look at this the recent papers of end-to-end autonomous driving, especially on this NavSim challenges and also the case one of the most popular and state-of-the-art imitation learnings of diffusion-based imitation learning model, and you can see that it's mostly they're the losses are from the human demonstration, but it's also mean that we are limited by human demonstration. So actually beyond the human demonstration, many trajectories are viable. So if we look at a robotics, the typical reinforcement learning algorithm, like we have an environment, we have an agent, so the agent will generate an action and the environment will provide the rewards. And in autonomous driving, we can also formulate these patterns in terms of the Napsim challenge. So the agents will generate some actions and our environments will provide this reward as a provides EPDMS as a reward to the autonomous our agents. So here, therefore, we came up with a pseudo reinforcement learning in autonomous driving, because like it's a little bit tricky that because like in autonomous driving, the trajectory we don't have like two-dimension waypoints instead of like complicated robotics action. So what we can do is that we can directly use predefined actions. So and then we don't have to use the loop. We can just do it in one inference, meaning that we can directly generate all the actions, almost all the actions and all the rewards, and then we can select the action according to the rewards. So here's here's the motivations of our methods. So after we get this this pipeline from robotics, we come up with this GTRS. So we have a trajectory generator, which contains a fixed vocabularies, and we also have a trajectory rewards model. It's the knowledge distills from the EPDMS. So sorry. Yeah, I'll welcome to present the details of the method. Thanks.
Okay, so inspired by diffusion policy models, we enhance our static predefined trajectory vocabulary by injecting some dynamic scene-aware trajectories generated by a diffusion model. These diffusion-generated candidates are tailored to, this diffusion-generated candidates are tailored for the current driving context and provide some additional behavior diversity that the static site may miss. By combining both the fixed and the learned trajectories and evaluating them with our behavior quality score, we achieve better coverage of viable actions. This hybrid approach leads to measurable improvements, yielding a 1.1 point gain in EPDMS, demonstrating that diffusion trajectories effectively complement the static vocabulary. To further improve the performance of our current pipeline, we propose GTRS dense. We train the trajectory score with a super dense vocabulary to enhance its generalization ability, enabling the model to develop strong scoring abilities across a wide range of trajectory distributions. These trajectories are passed through a dropout layer for regularization. Only a random half are remained during each iteration, which prevents overfitting to some specific trajectory patterns. Our experiment results show that the dropout operation improves the generalization ability by improving 1.4 EPDMS. To further improve the generalization and robustness, we apply sensor augmentations and the causal firing refinement strategy during training. Specifically, we propose GTRS-aug, which simulates domain shifts between real world and the simulation environment by introducing some perturbations such as the viewpoint rotation changes. These augmentations prevent the scorer from overfitting to specific sensor patterns and encourage the model to make consistent judgments under diverse visual conditions. We also develop a refinement training mechanism focused on fine-grained trajectory discrimination. It incorporates an additional transformer decoder that progressively refines trajectory scores only for top K most promising candidates, enabling the model to capture subtle differences between the similar trajectories. As a result, the model becomes more resilient to sensor variation and achieves 2.8% gain in EPDMS. To maximize the performance of our current pipeline, we assemble both the trajectory generator and the trajectory scores. By combining diffusion policy generator trajectories with a fixed vocabulary and evaluating them using multiple complementary scores such as GTRS dense and GTRS aug we introduced before, we capture diverse perspectives on trajectory quality. Each score contributes to unique strengths such as robustness generalization or sensitivity to sensor variation. And assembling allows us to make more reliable, well-rounded decisions. This approach significantly boosts overall planning quality, achieving a final 49.4 EPDMS and defining the 2025 champion solution GTRS. Here's the video demonstration. Here are our group members. Thanks for your listening, and please scan the QR code for more details. Thanks.
Thanks for NASIM team challenge organizer and team leader for sharing this year's end-to-end driving progress on the NASIM level. And so we have a short break for 5 minutes, and at 10:20 we will have Professor Felix presenting his work at this workshop. Thank you. Yeah. Hello, Antonio. Nice to meet you. Yeah. Okay. You're using your laptop.
Hi, nice to meet you.
I remember you have video to play, right?
Yes. That's yes. Okay. So. Oh, it's good. Oh, yeah.
Well done.
Disappear.
Okay.
We do that jumping to Euro.
Yeah.
It's the,
Yeah. Yeah. No, that's good. That's good. Yeah.
Use the microphone. Speaker, so we use that. GTRS doesn't have
Understand. It took so long. Yeah.
I think you also had some discussions with.
Yeah. We should so finish this project.
Yeah. Come first, and do more master.
Yeah. Yeah.
Start with.
your is set. Yeah. Okay. I think we can do that. Yeah, because of this. And network speaker basically cover full room. We do to use the audio to errors. We need the. We see. So maybe the issue solved. Okay, let me do it. So send your link.
Yeah.
It goes to camera.
Yeah.
You have my email.
Yeah.
No,
I remember
they
that
did not
we
come in.
were speaking.
Yeah.
Okay.
Okay.
They did not come back. Yeah.
I can help you set up.
Oh, yeah, let me. Do you have an HDMI?
Yeah.
Yeah. I'll just, yeah.
This is for the audio, so the
Oh.
the microphone. I mean.
Oh,
Yeah. So when you screen sharing, it will record your audio for the microphone. Yeah.
Right, so we are continuing with Professor Felix Heiden talking on scalable autonomous driving